continue our discussion on the enhancement MOSFET. The most important feature to understand, the most important characteristic rather to understand the behavior of any electronic device is the IB characteristics, current voltage characteristics. So, we talk about drain and transfer characteristics. Characteristics of E-MOSFET, enhancement mode MOSFET. To understand these characteristics, it is of advantage to keep the geometry of the device in the mind, and to remind you that the geometry is like this. This is the P substrate, for example, P silicon, and this is moderately doped N type. This is the metallic contact, and so it makes it source. This is the SiO2 layer. This structure we have talked, and this is another electrode, then metal electrode here, and this is drain, and this is the metal electrode on the gate. So, this is the gate electrode. Then we establish a potential difference between source and drain, and another voltage, a positive voltage between source and gate. This is gate, and once VGS, gate source voltage, is greater than the threshold voltage which gives the channel, which creates the channel by the inversion layer. This we have discussed in details, that how in enhancement MOSFET a channel is created. There is no implanted channel. Initially there is no channel, but channel is created between the drain and source here. This is the channel, and conduction will occur under these conditions when VGS is greater than or equal to the threshold voltage. Then the conduction between drain and source will occur, and this will be controlled by the voltage VGS between gate and source. So, now we are in a position to draw the characteristics. We plot these characteristics, and they are between the drain current ID in milliamperes, and this is VDS, the voltage between drain and source. This is in volts, and these characteristics come out to be like this. Like that, and this is VGS. VGS here, for example, 2 volts, 4 volts, 6 volts and 8 volts. These are the drain characteristics, as we call, for the E MOSFET. Now, and these currents, as we have talked earlier, that this current, drain current, exists only for voltages in excess when gate source voltage is equal or greater than the threshold voltage required for the channel creation. Now, these characteristics can be divided into 3 regions. Here the loci of these points where a kind of saturation region starts, this as usual we have seen earlier as well, VDS has to be equal to VGS minus VT. And now these are 3 regions. One region VT is normally this threshold voltage is of the order of 2 volts or less, and so this region is where VGS is less than VT, and this is the cutoff region. And on the left of this dividing line, this is the ohmic region. And this is the saturation region. This is saturation region. So, these are the 3 regions in which we can divide these current voltage characteristics. Now, we will talk about these 3 regions one by one and show the behavior of the device under each characteristic. First, we take the ohmic region. Remember, this is the region which is the ohmic region, and the drain current here in this region, the drain current ID is controlled by the drain source voltage by VDS for gate source voltage greater than VT, and the current can be expressed, ID, the drain current is given by K twice VGS minus VT VDS minus VDS square. This is the expression which gives the dependence of drain current in this region, drain current on VDS. So, we can see, actually we can take VDS out here, K is a constant and we will define it, what is the value of this. So, this can be, from this expression we can write that drain current is proportional to VDS, and this constant K, this is true for under this condition, and in the above equation, in this equation, K is a constant, a device constant, and this can be shown to be equal to K can be shown to be equal to mu n Cm W by L. This is the expression which defines this constant K, the device constant for the E MOSFET, and in this L, L, L is the channel length, channel length. Typically, this L is of the order of 10 micrometer. The structure of the device is like this. This is gate, this is source, and this is that metallic contact, and this is drain, and this is the metal contact, and this is L, channel length. And between drain and source here, drain and source, this is this red one, this is the channel. So, this is the channel length L, this is channel length L, and W is here. W is channel width, channel width, and typically W is of the order of 100 micrometer. And mu n, this mu n is surface mobility of electrons, because we are talking of normally used n channel MOSFET, E MOSFET, and so this channel is containing electrons. So, we are concerned with the surface mobility of electrons, and this is around 600 centimeter square volt second. If we compare this with the bulk value, and this is the bulk value is, it is much less, it is much less than the bulk value mu n, which is around, which is 1500 centimeter square volt second. The surface mobility of electrons, this is much reduced, and the reason is the mu n is quite low due to this reason. The reason is the scattering of electrons from surface and trapped, and from trapped charges in the oxide layer. What we are saying? We are saying that mobility of electrons normally in the bulk material is around 1500 centimeter square by volt second, and but here this is a kind of a very thin layer. So, we talk of the surface mobility mu n, and which is around 600, which is much less than, and the reason is the scattering of these electrons from this surface and from the trapped charges in the oxide layer. Cm, we have defined W, we have defined length, we have defined mu n, then this Cm is this is equal to epsilon s epsilon 0 by T x, where this is the epsilon s, this is the dielectric constant of the oxide layer, which is typically around 3 and or maybe more actually, and epsilon 0 is the permittivity of free space, which is 8.85 10 to the power minus 14 farads per centimeter, and TOX, this is thickness of oxide layer, and typically it is a fraction, of a micrometer. So, this is about the constant K. Sometimes K is defined in another way. This is one possibility. Often it is defined when all geometrical parameters are known, but there is another way of defining constant, K, and this is K is equal to ID on VGS on minus VT square. These parameters can be obtained actually from the IV characteristics. For example, here if this is around 10 milliamperes, then this becomes ID on becomes 10, and if this is for 8 volts, then VGS is 8 volts and this is VT. So, if we use this expression, then we should know the geometry of the device completely, and if in the absence of that, if they are not available, then we can use this expression for the constant K, where the parameters can be determined from the characteristics of the drain characteristics. So, this was about the ohmic region. Here we finish the ohmic region, and then we move to, we remember this K because this will be used even in saturation region and so on. Saturation region of these characteristics, where the device, whenever we want to use it in amplifying mode as amplifier, then we have to operate it in this saturation region. This we have talked in the junction field effect transistor, we have talked in the depletion mode MOSFET, and now in the drain in this E MOSFET also the same thing. So, next is saturation region. Saturation region. In the saturation region, in this region, VDS is greater or equal to VGS minus VT. This is, this is the boundary here, which is defined by this. So, in the saturation region, VDS has to be greater than this parameter, this, and ID is given, the drain current is given by K, the constant which we have defined above, and VGS minus VT square, where VT is around 2 volts or less. Now, from the characteristics, when we elaborate this saturation region, then actually here of course, they are almost horizontal, but there is a slight angle. That means, here as we have shown that drain current is independent of VDS, but it does depend, it also shows independent, the drain current is independent of the drain source voltage, but we will see little later when we go in greater detail, then there is a mild dependence. So, here in this region there is a weak dependence or no dependence of ID on VDS. This equation is very important and it gives rise to drain characteristics and the transfer characteristics. So, we talk about from here, this is constant for a device and K is a constant. So, ID is a function of VGS. So, this is the equation of a parabola, and drain current, the output current, and input voltage is the gate source voltage. So, from here we can get transfer curve, transfer curve, and these curve, this is from equation, this x as we have said, we can plot, and this is this. This is Vt, VGS, and this is ID, milliamperes, and this is for example 10, 5 and so on, and this is VGS. So, this is the the transfer curve for constant VDS. It is very important curve. Let me recall and remind you that beta, the current gain, was one of the most important parameter for a bipolar transistor BJT. FET is a current is voltage operative device, and here the dependence of output current on input voltage, and input voltage is gate source voltage, output current is drain current. So, we are more concerned with the dependence of this current on this voltage. Now, from here we can get, we will talk little later, that on the operating point Q, by putting a tangent we can find out the most important parameter for these devices, and that is Gm, which is transconductance that we can get from here. Now, we said that in these in the saturation region, the drain current is almost independent of VDS. Here the current is same almost as here, but as was pointed out that there is a weak dependence, and if we look into this weak dependence, we elaborate these characteristics, then we get this. When we connect at the back, this is drain current, this is VDS, this is VGS, this is 0, then this cuts this VDS axis on the negative side at minus 1 by lambda. This this gives early, this 1 by lambda is called early voltage. Early is the name of the scientist, early voltage. And this is equivalent to the channel width modulation, and which is almost like the base width modulation in BJT. So, this is the, when we take into account this weak dependence of drain current on VDS, then this parameter can be taken, and that gives, this is this voltage, early voltage 1 by lambda, this is of the order of 0.01 volt to 0.03 volts. Of course, this is on the negative side, and the ID dependence, when we consider this early voltage, then it is K VGS minus VT square 1 plus lambda VDS. This becomes, this is the more accurate expression, which gives more accurately, expresses more accurately the drain current dependence on VDS. In normally, as we have done earlier, this is a very small parameter, this is small, as we have seen, very small. So, often this effect is neglected, and ID practically is taken as VGS minus VT in the saturation region, as we have been using. And finally, in these characteristics, there is a cutoff region. We said that characteristics can be divided into 3 regions: the ohmic region, the saturation region, and here is the cutoff region, this region. So, cutoff region in the cutoff region, VGS is less than VT. That is, this channel is not formed, the voltage is insufficient to form the voltage, to form the channel. So, the channel is not formed, and in the absence of the channel, there is no contact between drain and source, and hence ID, the drain current, will be 0, and for all values of VDS, drain current will be 0, and the device is said to be off. Device is off. So, this is about the characteristics of the drain characteristics, the transfer characteristics of the device, and the device under discussion, just to remind you, is E MOSFET, enhancement mode MOSFET. And now we go further and we take biasing of FETs and MOSFETs. That is the next thing which we are starting, that is biasing of FETs in general that includes and MOSFETs. This is the next topic. Why do we require to bias the device? I am sure by now you understand that. It has been said that when we want to operate the device for amplifying purposes, then the device has to be operated in the saturation region. When the device is to be operated in the as a switch where on and off, then it has to go in the cutoff region. So, the region may be cutoff and saturation and or the cutoff and ohmic region. So, these are the two regions which are used only when the device is to be used as a switch, but for amplifying purposes the linear relationship between the between VDS and ID is required, and when we have a constant VDS, then as we increase the gate source voltage, the output current will vary and the device will work. So, we have to bias the device. Now, for the sake of completeness, I must say that one of the biasing possibility is a fixed bias. Fixed bias. What is fixed bias? Let us take as an example first the junction field effect transistor. This is source, this is drain, this is gate, and this is VDD, and here this is the resistance RD and the current ID flows through it, and here there is a voltage drop VDS, and this is VGS. This is for N type JFET. We can draw, we will remember that for N type JFET the gate has to be negatively biased. It should have a negative potential with respect to source. So, this battery supplies VGS, and we can draw this plot. There is no reason to elaborate it, this we have talked. For example, this plot can be shown to be like this. Same thing. So, but there is no need to show this like this. This is always implied that one terminal of the battery is here, other is grounded. So, we continue with this simpler design which is much more frequently used than this. So, this is the fixed bias, and here why fixed? Here this bias is provided by this battery VGS, and it is in no way connected with the output variations in the output circuit. So, it is fixed. What is the meaning of fixed? The fixed bias, it is called fixed bias because of this reason, that it will not provide any stability to the circuit against the variations in the device or in the temperature. Device variations may occur because of two reasons basically. For the continuous use of the device, sometimes their characteristics change. This is one reason, which is called aging. And for the same reasons, the value of this resistance for continuous use, this may change. So, because of this variation or temperature variations are very common in electronic circuits, and that will change the characteristics. And unless precaution is taken, this point we have discussed in much greater details in the bipolar transistor, that fixed bias is no good. So, there are two drawbacks in this. One, two drawbacks in fixed bias. One is, it does not take any corrective measures for any variations in the device parameters or temperature. So, no guard against any variations, temperature or device parameters. Another important parameter, another limitation is that it needs two batteries. One is here, the other is here, VGS, two batteries. So, in most circuit, the use of two batteries, if it can be avoided, should be avoided. So, there is no requirement of additional battery. So, these are, remember, fixed bias is not a proper choice for biasing. This is fixed bias. Here the biasing voltage is independent of any kind of variations, either in the temperature of the circuit or in the device parameters. The most important device parameter is transconductance, which has some dependence on temperature, or it may change because of the aging effects. So, this is one region. Another region is the use of two batteries. So, fixed bias is not used. This circuit I have drawn for this N JFET. This can be shown for P JFET also, simply by reversing the sign of this battery. That means for P JFET, this will be this is VDD and this is VGS, this is G, RD, ID, and this is source. So, this is the fixed bias for P type junction field effect transistor, P channel. That was for N channel, but N channel is much more widely used than this. So, then what are the choices for biasing? The fixed bias, for the reasons we have discussed, is not a good biasing scheme. There are two biasing schemes which are widely used. Two biasing schemes. One is called self bias, and the other one is voltage divider bias. Self bias and voltage divider bias, these are the two schemes which are most widely used. So, we take one by one these two practically used biasing networks. First we take self bias. Self bias. Here the circuit is simple and this is this. This is the self bias. Why it is called self bias, that we will explain. And here this is VGS. Voltage between gate and source, this is VGS, and which we are marking as plus here and minus here. Now, here ID, the drain current, flows through this resistance, drain resistance RD, source resistance RD, and this is the voltage drop between drain and source. And so, actually we can write a voltage summation at the output circuit, drain, source. The voltage, Kirchhoff's voltage law, we apply at drain source circuit, and we get what we get. This is summation. So, we start with VDD, this is equal to ID RD plus VDS plus the same current flows here ID. So, IDRS. This can be written as VDD equal to VDS plus ID RD RS, and from here this equation we will use later, that VDS is given by VDD minus ID RD plus RS. If we call this equation 1. If these resistances are known, current is known, then what will be the voltage drop VDS, which is a must. We must know VDS, that will decide our the drain current. Now, in the gate source circuit here, let us say the current Ig flows, then in the gate source circuit here there are the voltage drop across this because of Ig, the voltage drop across Rs. Now, this point which I am now discussing will illustrate that why it is called self bias and how it provides the stability to the circuit. The operating point once chosen will remain stable against the device temperature variation or variation in device parameters. So, the three voltages are involved, one across this because of current Ig and this voltage VGS, and the drop across Rs because the circuit, input circuit, the gate source circuit is this. So, here summation or Kirchhoff's voltage law gives VGS plus IDRS minus IG RG equal to 0. And in FETs we know that this current, the gate current, is normally very close to 0. It is in picoamperes or less in well designed devices. So, in FET or even for MOSFETs, the Ig gate current is 0. So, when we put Ig 0 here, we get VGS plus ID Rs equal to 0, or from here, or VGS is equal to minus RSID. This is the gate source voltage which we were providing in the fixed bias circuit by another battery. In the self bias, that is available as the voltage drop across this resistance Rs. That is why it is called self bias. There is no extra battery to provide this voltage VGS, but it is available as a drop across this. Now, several important features can be discussed with this. One is, if Rs is 0, then actually no voltage, the voltage VGS will be 0. So, we will be in the cutoff region. So, in self bias, Rs, the value of Rs decides the value of this voltage. Of course, that will depend on ID as well. So, this total drop across this resistance gives the voltage. Now, we say that self, this is very important, self bias stabilizes the operating point. Once we have chosen the value of, for example, this is the operating point here. So, we have these all these voltages and currents. The value of VDS is fixed. This is called VDSQ. This is called IDQ. At the Q point, what is the voltage drop and what is this and how much is the VGS, all parameters are known. So, this operating point once chosen will be stable against all kinds of variations. Let us look at this point. Suppose temperature increases, temperature of the ambience where the circuit is working or of the circuit parts, because there is always the resistances are there, and whenever the current flows there is a heating, and I square R, that is the heat thermal energy generated. So, the temperature changes. Semiconductor devices, MOSFETs are semiconductor devices. So, normally the drain current will increase. So, if drain current increases, then in a fixed bias circuit like this, if the drain current increases, that will change this VDS and of course drain current, meaning the operating point will shift. The drain current will increase, and so the operating point will shift. There is nothing to take corrective measures in the fixed bias, while in the self bias, if this current increases, then this voltage will be more negative. If this increases, this will be more negative, VGS more negative. If you remember the characteristics, for example, of a N JFET, which is under present discussion, more negative means ID will fall. The characteristics were like this. This is minus 4 volts, minus 3 volts, no, minus 3, minus 5, minus 6 ID. So, this way, if this current increases, then this will reduce, that means it will make gate source voltage more negative, and hence this will take the corrective measures. So, whatever are the reasons for the variation, they will be taken care of. If for some reasons the parameters fall so that the drain current falls, if drain current falls, then this will be less negative, and hence the drain current will stabilize, will be the fall in the drain current will be checked by this voltage drop, because this voltage drop is a function of ID, and this voltage is the part of the input circuit, the gate source circuit, and hence self bias is very widely used. Here last point, that Ig we have taken 0, so no current flows through this Rg. So, Rg is that acts, it is a high voltage probe, there is no current through it, and hence Rg can be taken in the range of 50 kilo ohms to 100 kilo ohms. So, all the shortcomings of the fixed bias are removed in the self bias, in this self bias circuit, and this is widely used with the junction field effect transistors, and it can be used for the depletion MOSFET also, because there also the proper sign of the voltage required is this. We will continue.